Black holes, how big can they get? Is there a universal size limit? What happens if a black hole gets too big? Black holes are perhaps the most mysterious and awe-inspiring entities in the universe. These invisible titans of the universe have an unmatched superpower: gravity. They have a gravitational pull so intense that nothing, not even light, can escape once it crosses their event horizon. They can devour stars, distort time, and warp space. But even with their seemingly endless ability to grow, you have to ask the question, how big can a black hole actually get? Is there a limit to their size? Or can they grow forever, endlessly absorbing matter and light in a cosmic feeding frenzy? To answer these questions, we need to start with how black holes form. Imagine this: a massive star, 25 times the mass of our Sun, collapsing under its own gravity after burning through its fuel. It compresses itself into a point of infinite density referred to as a singularity. This is where the numbers become insane. Our Sun has a diameter of 865,000 miles, so imagine a star, 25 times more massive, collapsing into a black hole with a diameter of only 100 miles. Around this singularity is the event horizon, the boundary beyond which escape becomes impossible. But these stellar mass black holes are the lightweights of the black hole family. There exist black holes that are so massive that they are called supermassive black holes. These are the ones that sit at the heart of galaxies, including our own Milky Way. These celestial monsters weigh millions to billions of solar masses. Sagittarius A, the supermassive black hole at the center of our galaxy, has a mass equivalent of about 4 million suns. But even Sagittarius A can be considered a small black hole. Ton 618, the largest quasar ever found, is estimated to be 66 billion solar masses, and Phoenix A is estimated at around 100 billion. Black holes grow over time through a variety of mechanisms. They pull in gas and dust from their surroundings, forming a blazing hot accretion disk that spirals inward, feeding the black hole. And don't think falling into a black hole is remotely possible. The accretion disk can be over 10 million degrees Celsius. Black holes can merge with other black holes, creating massive collisions that send gravitational waves rippling across the universe. And if a star ventures too close, it gets torn apart and consumed, its mass adding to the black hole's already staggering size. But even with all this cosmic consumption, one might think black holes could grow forever, but the universe has built-in checks and balances. Everything, it turns out, has a limit. One of these is the Edington Limit. As matter falls into a black hole, it doesn't disappear quietly. The process generates powerful radiation from the accretion disk, and this radiation pushes outward. At a certain point, this outward radiation balances the inward gravitational pull. If the black hole tries to consume matter faster than the Edington Limit allows, the radiation pressure pushes the material away, effectively slowing or even halting the black hole's growth. The Edington Limit doesn't set a hard cap on size, but it definitely puts the brakes on runaway growth. Another limiting factor is fuel. A black hole can only grow if there's something nearby to feed on. In the crowded, gas-rich centers of galaxies, black holes can dine like royalty, growing into the supermassive giants we see today. But out in the galactic suburbs or between galaxies where matter is scarce, black holes can go without consuming for millions of years. If they can't find more mass to consume, their growth stops. But even with these limits, black holes have reached unimaginable sizes. The black hole at the center of M87, the one captured in the first ever image of a black hole by the Event Horizon Telescope in 2019, has a mass of about 6.5 billion suns. It still leaves the question, how do such behemoths come to exist? The most likely answer is time. In the early universe, galaxies were denser, closer together, and brimming with gas. Black holes in these conditions had more opportunities to merge and feed, growing rapidly over billions of years. It could also be that theoretical black holes called primordial black holes might have formed, not from dying stars, but from the chaos of the early universe itself. If these black holes actually existed and avoided evaporation through Hawking radiation, they could have had a head start on mass accumulation and become the giants we see today. But evidence for primordial black holes has not been found, and their existence is not confirmed. There's also a theoretical breed of black holes called stupendously large black holes, or slabs, which could be hundreds of billions of solar masses. While entertaining to consider, no observational evidence supports their existence as of yet, and it's unclear whether the universe would even allow such massive structures to form. Another speculative limit could come from space and time itself. Some physicists believe that beyond a certain size, a black hole's effect on space-time could become so extreme that growth beyond a certain point is somehow not allowed. It's possible that quantum effects or space-time geometry enforce a cosmic ceiling. There's also the concept of cosmic censorship, the idea that singularities must always be hidden behind event horizons. If growth began to expose them, nature might intervene in ways we don't yet understand. So, how big is too big for a black hole? It's still an open question. We know that black holes can grow into the tens of billions of solar masses, and it's theoretically possible they could grow even larger given enough time and material. But between the Edington Limit, the finite availability of mass in the universe, and the strange geometry of space-time itself, it seems unlikely they can grow without end. The largest black holes we've discovered are cosmic monsters, but these monsters live in a universe governed by laws, and in those laws, there are boundaries. We may yet discover larger black holes, perhaps even slabs if they exist, but there will almost certainly be a point at which even the hungriest black holes must stop consuming. Black holes are complex, rule-bound objects, shaped by the same physics that govern stars, galaxies, and the fabric of the cosmos. The universe, it seems, knows how to build a giant, but it also knows how to stop them from reaching a size that could theoretically threaten the very fabric of space-time. I'd like to thank you for spending time with us, investigating how massive black holes can become, and I invite you back for our next episode of A Godless Universe.